The Hardening, a novel. Being a complete and accurate account of the hydration of Portland cement concrete, with special attention to placing, finishing, curing, and the professional life of Eno Mikagan, concrete foreman. Chapter 1. The Morning. At 6:47 in the morning, Eno Mikagan arrived at the construction site. He was wearing his orange vest, which he put on in the same order every day: left arm, right arm, zipper. The zipper sometimes caught at the bottom. It did not catch today. He noted this without particular feeling. The site was a two-story commercial building in the eastern part of the city. The ground floor would eventually become a hardware store. The upper floor had not yet been decided. Eno did not find this ambiguity troubling. His job was the concrete. What came after the concrete was someone else's concern. He set down his thermos on the portable table next to the side office. The thermos was blue and had a small dent on one side from an incident 3 years ago involving a ladder and a moment of inattention. He poured coffee into the lid cup. The coffee was the same temperature it always was when he arrived, because he filled the thermos at home at 6:15, and the drive took 22 minutes, and the walk from the car took 4 minutes. He had never calculated this. He simply knew. Pertti Saarinen, who operated the concrete mixer, arrived at 6:51. He nodded at Eno. Eno nodded back. They had worked together for 11 years. In those 11 years, they had developed a vocabulary of nods so precise that verbal communication before 8 o'clock in the morning was largely unnecessary. The morning was overcast. This was, from a concrete perspective, acceptable. Direct sunlight in summer could accelerate surface drying and lead to plastic shrinkage, cracking if the fresh concrete was not properly cured. An overcast sky reduced evaporation. Eno was aware of this. He looked at the sky the way a person looks at a colleague they approve of but would not describe as a friend. The concrete truck was scheduled to arrive at 7:30. It was now 6:53. There was time. Chapter 2. What concrete is. Concrete is, in the most fundamental sense, a mixture. It is not complicated to describe, though it is not simple to make well. The primary ingredients are Portland cement, water, fine aggregate, and coarse aggregate. Sometimes there are admixtures. Eno thought about admixtures the way some people think about condiments, useful in context, but not something to be applied without reason. Portland cement is itself a mixture, produced by heating limestone and clay in a kiln to temperatures around 1,450 degrees Celsius. The result is a substance called clinker, which is then ground into a fine powder with a small amount of gypsum. The gypsum regulates setting time. Without gypsum, the cement would set too quickly to be useful. The fine aggregate is sand. The coarse aggregate is gravel or crushed stone. These components do not contribute to the chemical processes that make concrete hard. They are, in a sense, passengers. But they are important passengers. They provide bulk, reduce cost, and affect the workability and final strength of the mix. A concrete made without aggregate would be expensive, prone to cracking from shrinkage, and generally inferior. Water is perhaps the most consequential ingredient. Too little, and the mix is unworkable, a dry, crumbling mass that cannot be placed or finished. Too much, and the concrete will be weak, prone to cracking, and susceptible to freeze-thaw damage. The ratio of water to cement, the water-cement ratio, often abbreviated WC, is one of the most important numbers in concrete technology. Eno had known this number for most of his adult life, with the same quiet familiarity that one knows one's own birthday. The process by which cement and water combine to form a hard, durable mass is called hydration. It is a quadratic reaction, exothermic in nature, meaning It releases heat. This heat can, in large pores, cause problems. In small pores, it is simply a fact. Hydration is not instantaneous. It begins within minutes of contact between cement and water, but it continues for days, weeks, and in a diminishing way, years. This is the central drama of Aino's professional life, such as it was the transformation of a wet, formless slurry into a stone-like solid. He had watched it happen thousands of times. It never surprised him. This was, he felt, appropriate. Surprises in concrete work were rarely good. Chapter 3. The truck arrives. The concrete truck arrived at 7:28, which was 2 minutes early. Eno noted this. Perty also noted this. They exchanged a brief look that communicated something in the range of mild satisfaction, though neither would have described it that way. The truck was a standard transit mixer, its drum rotating slowly as it came down the road. The rotation during transit serves to keep the concrete from segregating, to prevent the heavier aggregates from sinking to the bottom and the water from rising to the top. This rotation also continues mixing, which is why transit mixed concrete can be delivered over relatively long distances without significant loss of quality, provided the transit time stays within acceptable limits. The acceptable limit is generally around 90 minutes from the time of first water contact, or a maximum of 300 revolutions of the drum, whichever comes first. The driver, a man named Juhani, whom Eno recognized but did not know well, backed the truck into position with a series of small reversals. He checked his mirrors frequently. He did not hurry. The drum continued to turn. Eno checked the delivery ticket. He checked the specified mix design against what had been ordered, AC25, 30 concrete, with a maximum water-cement ratio of 0.55, a minimum cement content of 300 kilograms per cubic meter, and a target slump of 100 millimeters. The slump was a measure of consistency of how much the fresh concrete would settle when an inverted cone of the material was removed from around it. A slump of 100 millimeters meant the concrete was workable but not soupy. This was what they needed for a floor pour. He performed a slump test. He filled the cone in 3 layers, rodding each layer 25 times with a steel rod to consolidate it. He removed the cone in one smooth upward pull, taking between 2 and 5 seconds as specified. He measured the slump 95 millimeters. This was within acceptable tolerance. He wrote it on the form. Juhani watched him do this from beside the cab. He had watched slump tests performed hundreds of times in his career as a driver. He did not find them interesting, but he understood their purpose and respected the care with which men like Aino performed them. That was the word care, not passion, not enthusiasm, care. Chapter 4. The Chemistry of Setting. When Portland cement meets water, a series of chemical reactions begin. These reactions are not all of the same kind, or the same speed, or the same consequence. They unfold over time in a sequence that is somewhat predictable and largely well understood, though the precise details of some reactions remain a subject of scientific study. The primary compounds in Portland cement clinker are, in order of typical abundance, alate, belate, calcium aluminate, and tetracalcium aluminovrite. Alate, whose chemical name is tricalcium silicate, is the most important. It reacts quickly with water and is responsible for most of the strength gain in the first few weeks. Belate, or decalcium silicate, reacts more slowly and contributes to long-term strength. The aluminates react fastest of all, which is why gypsum must be present without it. The flash setting of the aluminate phases would make the cement unusable. The hydration of alate produces 2 products, calcium silicate hydrate, abbreviated CSH, and calcium hydroxide, also known as Portlandite. CSH is the binding agent. It is a poorly crystalline gel-like substance that forms a dense interlocking network as it precipitates. It is, in a sense, the glue. Calcium hydroxide is a byproduct. It is useful in some secondary applications. It gives concrete its high pH, which protects embedded steel from corrosion, but it is not itself a binding agent. The initial period after mixing, during which the concrete is workable and can be placed, is called the dormant period or induction period. During this time, the hydration reactions proceed, but slowly. The concrete remains plastic. Then, typically within a few hours, the reactions accelerate. The concrete begins to stiffen. This is the initial set. Shortly after, it becomes rigid enough that it will no longer be disturbed by normal handling. This is the final set. Temperature affects this timeline. Warmer temperatures accelerate hydration. Colder temperatures retard it. Below about 5 degrees Celsius, hydration essentially stops. This is why concrete poured in winter requires special precautions: insulating blankets, heated enclosures, heated mixing water, or accelerating admixtures. Eno had poured concrete in February. He did not remember it fondly, but he had done it correctly. After the final set, hardening continues. Concrete gains strength steadily over the following days and weeks. The standard reference point for concrete strength is the 28-day compressive strength. This is the value specified in structural designs, the value measured in tests, the value by which concrete mixes are characterized. But concrete continues to gain strength beyond 28 days, more slowly, and for a long time. A very old concrete structure, kept moist, is often somewhat stronger than it was at 28 days. Not dramatically so, but measurably. Chapter 5. Placing the concrete. The pour began at 7:41. Eno had positioned the chute so that the concrete fell vertically into the form, which was the correct way to do it. Dropping concrete from an angle, or allowing it to flow horizontally across a long distance, could cause segregation, the aggregates separating from the paste and producing an uneven, potentially weak result. Perty operated the vibrator. The vibrator was an electric device with a head that vibrated at high frequency when inserted into the fresh concrete. Its purpose was to consolidate the concrete to eliminate air voids and ensure that the mix flowed around all the reinforcing bars and into all corners of the form. Without consolidation, a concrete pour could contain honeycombing voids filled with air rather than paste, which would significantly reduce strength and durability. The vibrator head was inserted at regular intervals, approximately 450 millimeters apart, a spacing roughly equal to 1.5 times the radius of action of the vibrator head. Perty had been doing this for years. He did not measure the spacing. He knew it the way a musician knows a melody, not consciously, but reliably. The concrete flowed. It was gray. It was wet. It had the look of something between a thick soup and a wet sand, which was in a way exactly what it was. Eno watched the level rise in the form. He watched for any sign of leakage at the form joints. None appeared. He watched the surface for any indication of segregation. There was none. The morning remained overcast. The temperature was 12 degrees Celsius. These were good conditions, not ideal, because concrete preferred something closer to 20 degrees for optimal hydration, but good. The target strength of C25-30, meaning a characteristic compressive strength of 25 megapascals on 150 millimeter cubes, or 30 megapascals on 150 millimeter cylinders, was achievable under these conditions without special measures. Juhani monitored the drum. When the load was nearly depleted, he rinsed the chute with water, which he discharged into a container, not onto the ground. Environmental regulations on wash water had changed over the years. Juhani had changed his habits accordingly. He was a practical man. Chapter 6. Finishing. After the concrete was placed and consolidated, it required finishing. For a floor slab intended to bear pedestrian and light vehicular traffic as this one would, given that the ground floor was destined to be a hardware store, the surface needed to be flat, smooth enough for practical use, and free of surface defects. The first step was screeding, drawing a long straight board, the screed across the top of the form to remove excess concrete and establish a level surface. Eno and Perty did this together. Eno held one end of the screed, Perty the other. They moved it across the slab in a back-and-forth sawing motion, working steadily toward one end. It was not a complicated task, but it required consistency. An irregular or inattentive screeding motion would produce an uneven surface. After screeding came bull floating, using a large flat float on a long handle to smooth the surface further and embed the coarse aggregate slightly below the surface. The bull float passed over the concrete in overlapping strokes. This was Eno's task. Perty watched, and occasionally helped when the float reached the far edge of the slab. Then came waiting. This was, in Eno's experience, the part of concrete work that people who did not do concrete work most failed to appreciate. The fresh concrete had to reach a certain state before it could be further worked. Too early, and the finishing tools would tear the surface or push bleed water back into the concrete. Too late, and the concrete would have stiffened beyond workability. The right time could be assessed by pressing a thumb into the surface and observing the indentation. Eno pressed his thumb into the concrete at intervals. This was not impatience, it was monitoring. He had done it hundreds of times. The sensation of the concrete changing under his thumb, becoming less yielding, more resistant, the thumb leaving less of a mark each time, was one he could have described to a person new to the trade, but which that person would only have truly understood through repetition. When the time was right, and Eno judged it correctly, as he usually did, he began the final troweling. The power trowel, a machine with rotating blades, moved across the surface in overlapping circles, compressing and smoothing the surface layer. The sound was constant and mechanical. Eno guided the machine with practiced neutrality. Chapter 7. Curing. After finishing, the concrete had to be cured. Curing is, in its simplest description, the process of keeping concrete moist and at an appropriate temperature for a sufficient period after placing. This allows hydration to continue, which allows strength to develop. Concrete that dries out too quickly before hydration is sufficiently advanced will be weaker, more porous, more prone to surface cracking, and less durable than it could have been. There are several methods of curing. Wet curing involves covering the concrete with wet burlap or absorbent mats, which are kept continuously moist. Ponding, creating a small dam around the slab and filling it with water, is another method, suitable for flat, horizontal surfaces. Curing compounds, which are sprayed onto the surface and form a membrane that retains moisture, are widely used for their convenience. Eno generally used curing compound for floor slabs. He kept a spray tank for this purpose. He applied the curing compound immediately after finishing was complete. He walked backward across the slab in overlapping passes, holding the spray wand at a consistent height above the surface. The compound was a white pigmented resin-based product. The white pigment helped reflect sunlight, reducing temperature rise on warm days. It also served as a visual indicator that the compound had been applied uniformly. The recommended curing period for normal Portland cement concrete in temperate conditions is a minimum of 7 days. During this period, the concrete should not be subjected to loading that it is not yet strong enough to bear, to traffic that would damage the surface, or to conditions that would disrupt hydration, very high temperatures, freezing temperatures, or desiccating winds. The concrete would not be subjected to any of these things. The site was managed by responsible people who understood the requirements. This was not always the case in the construction industry. Eno had worked at sites where curing was treated as an afterthought, where forms were stripped too early, where slabs were loaded before they were ready. He had seen the consequences: plastic shrinkage, cracks, delamination, surface scaling, premature deterioration. He had said what needed to be said in those situations. Sometimes it was heard, sometimes it was not. He said nothing today, because there was nothing that needed to be said. He sprayed the compound, capped the tank, and walked to the edge of the slab to look at what they had done. The surface was smooth and uniformly gray. A faint sheen of the curing compound was visible. In a few hours, it would be invisible. The concrete would look like concrete, because it would be concrete. This seemed to him correct. Chapter 8. What happens next? In the hours following placement, while Aino and Perty cleaned the equipment, things were happening in the concrete that could not be seen. Hydration was proceeding. The calcium silicate hydrate was growing in tiny fibrous crystals, filling the spaces between and around the aggregate particles, interlocking, densifying, gradually replacing the water-filled voids with solid material. The concrete was warming slightly from the heat of hydration. In this pour a floor slab of modest thickness, perhaps 150 millimeters, the temperature rise would be modest, perhaps a few degrees. In a large dam or a thick foundation mat, the temperature rise could be tens of degrees, and managing that heat would be a significant engineering challenge. Here, it was not. The heat dissipated into the air and the ground below. The concrete was also undergoing some degree of shrinkage. All concrete shrinks somewhat as it dries, and as the chemical reactions of hydration proceed. This shrinkage, if restrained, causes tensile stresses, and concrete is weak in tension. This is why reinforcing steel is embedded in concrete structures. The steel carries the tensile forces, the concrete carries the compressive forces, and together they function as a composite material capable of bearing the varied loads of a real structure. The reinforcing steel in this slab, a standard mesh of 8 mm bars at 150 mm spacing in both directions, was already in place before the pour, held at the correct depth by plastic spacers. The concrete had flowed around it during placing and consolidation. Now it was encased. Over the next days and weeks, the bond between the concrete and the steel would develop as hydration proceeded, and the paste contracted slightly around the bars. This bond is one of the remarkable properties of reinforced concrete as a material. The concrete and steel adhere to each other with sufficient force that they can act compositely. They also, fortuitously, have nearly identical coefficients of thermal expansion, meaning they expand and contract together with temperature changes. If their thermal coefficients were significantly different, the bond would be disrupted by the cycling of temperature over a structure's lifetime. That they are compatible in this respect is fortunate, though it is worth noting that it was not known to be true when reinforced concrete was first developed in the 19th century. It was subsequently confirmed, which was reassuring. Eno was not thinking about any of this as he cleaned the screed board with a wire brush. He knew it, the way a person knows the grammar of their native language, not as a set of explicit rules, but as a deep, practiced competence. He brushed the hardening concrete from the board in efficient strokes. Then he hosed the board down. He stacked it with the other finishing tools. Chapter 9. Lunch. At noon, Eno and Perty ate lunch in the side office, which was a prefabricated container equipped with a small table, 2 plastic chairs, a kettle, and a calendar showing photographs of Finnish landscapes. The calendar was from a company that supplied cement. Eno had not selected it. It had simply appeared one day, as calendars at construction sites do. Eno had brought 2 open-face sandwiches, one with liver pâté and one with cheese, a small container of cucumber slices, and a banana. He ate these in order. Perty had brought a thermos of soup, which he poured into the thermos lid and consumed with a spoon he kept in his jacket pocket. This was his established practice. The spoon was a regular teaspoon, slightly bent from some long-past incident. They talked about the concrete. They talked about whether the temperature might drop overnight, and whether it would be worth covering the slab with insulating blankets. They concluded it would not be necessary. The forecast was for a low of 8 degrees, and with the curing compound applied, the slab would retain enough heat from its own hydration to stay above the threshold for hydration to continue. They talked briefly about a pour they had done the previous winter, when the temperature had dropped to -12, and they had heated the mixing water to 60 degrees, and covered the finished slab with 2 layers of insulating foam, and then still worried for 3 days until the temperatures rose. That concrete had turned out fine. Most concrete turned out fine when you took appropriate care. Perty mentioned that his car needed new brake pads. Eno said he knew a mechanic. Perty said he also knew a mechanic, but thank you. This exchange took about 45 seconds and constituted the social portion of the lunch break. After lunch, Ino went back to check the slab. He did not expect anything to have changed dramatically, but he believed in checking. He pressed his thumb to the surface. It left no impression. He walked around the perimeter, looking for cracks. There were none. The curing compound had dried to a barely visible film. The concrete was doing what concrete does, hardening quietly, without any need for attention. Chapter 10. The First Day's Strength. By the end of the first day, concrete of this composition, a water-cement ratio of approximately 0.55, a cement content of 300 kilograms per cubic meter, ordinary Portland cement would typically have achieved a compressive strength of around 8 to 12 megapascals. This was not enough to bear the design loads. It was, however, enough for the concrete to be self-supporting, enough that the forms could be left in place without concern that the concrete would slump or flow. Strength gain in concrete follows a characteristic curve, rapid at first, then progressively slower. The relationship can be approximately described by logarithmic equations, though these are idealizations. Real concrete in real conditions deviates from idealized curves due to temperature variations, moisture availability, and the inherent variability of natural materials. The cement industry has developed standard test protocols to measure concrete strength. The most common is the cylinder compression test. A concrete cylinder of standard dimensions, typically 150 millimeters in diameter and 300 millimeter tall in Europe, or 100 by 200 millimeters for smaller test specimens, is cast at the time of the pour, cured under controlled conditions, and then tested by loading it in a compression testing machine until failure. For this pour, Ino had cast 4 test cylinders. 2 would be tested at 7 days, 2 at 28 days. This was a standard protocol for a pour of this nature. The 7-day results would give a preliminary indication of strength development. The 28-day results would confirm compliance with the specified strength class. The test cylinders were stored in a dedicated curing box on the site, where they would be kept at a stable temperature and humidity until testing. They were labeled with a marker, the date of the pour, the mix designation, and a sequential number. Ino had written these labels clearly, as he always did. Illegible labels on test specimens had caused problems at sites he'd heard of. He did not allow this at his sites. The cylinders would be taken to a testing laboratory. A technician would cap their ends to ensure a flat parallel surface for loading. They would be placed in the testing machine. Load would be applied at a specified rate. The cylinder would fail suddenly, with a characteristic fracture pattern, and the peak load would be recorded. The strength would be calculated. Numbers would be written in a report. The concrete would either comply or not comply. In Ino's experience, his concrete complied. Chapter 11. 3 days later. On the 3rd day after the pour, Ino returned to inspect the slab. The weather had remained mild. The overnight temperatures had not dropped below 7 degrees. The conditions had been acceptable. He walked the slab with a straight edge, checking flatness. The specifications called for a surface tolerance of plus or minus 3 mm under a 3 meter straight edge. He measured at a number of points across the slab. All measurements were within tolerance. This was not surprising. The finishing had been done carefully, but it was good to confirm. There was a hairline crack near one corner. He crouched to examine it. It was less than 0.2 millimeters wide, running at approximately 45 degrees from the corner for about 300 millimeters. He recognized it, a shrinkage crack, concentrated at the stress concentration point of the corner. This was common. The specifications allowed cracks of this width. He photographed it for the record. He noted its location in his site diary. Had this crack been of structural concern, wider, longer, showing differential movement across its faces, he would have reported it to the structural engineer. It was not. He did not call the structural engineer. He moved on to the next check. He checked the compressive strength at 3 days by using a rebound hammer. This is an instrument that strikes the concrete surface with a spring-loaded mass and measures the rebound. The rebound value correlates, through empirical charts, to an estimated compressive strength. The estimate is not precise. The rebound hammer is sensitive to surface conditions, aggregate type and moisture content, but it gives a useful indication. The rebound readings, averaged across 10 measurements distributed across the slab, gave an estimated strength of 18 megapascals. This was consistent with what would be expected for a C2530 mix at 3 days in these temperature conditions. The 28-day strength, when tested in the laboratory on the cast cylinders, would be the definitive value. But 18 megapascals at 3 days was a reasonable intermediate result. Eno wrote it in his diary. Chapter 12. The 7-day mark. At 7 days, the 2 test cylinders designated for 7-day testing were collected from the site curing box by a technician from the testing laboratory. Eno signed the collection form. He noted the condition of the cylinders, no visible damage, labels intact in his site diary. The technician placed them carefully in a padded carry case and drove away. Eno watched the car leave the site and then returned to his other work. The laboratory was located in an industrial area of the city. It contained testing machines of various sizes, a curing room maintained at 20 degrees Celsius and above 95% relative humidity, and the precise and slightly oppressive quiet of a place where measurements are made and recorded. The technician who received the cylinders logged them into the system, verified the labels against the collection form, and placed them in the curing room. The following morning they were tested. The testing machine was calibrated. The cylinders were weighed. Their dimensions were measured. Their ends were checked for plainness, and where necessary, ground flat with a grinding disc. They were then placed in the machine and loaded at a rate of 0.5 megapascals per second until failure. The first cylinder failed at a peak load corresponding to a compressive strength of 19.8 megapascals. The second failed at 20.2 megapascals. The average was 20.0 megapascals. The characteristic 7-day strength expected for a C2530 mix under these conditions was typically in the range of 18 to 22 megapascals. These results were consistent with expectations. The laboratory report was issued the same afternoon and sent electronically to the project file. Eno received a copy. He read the numbers. They were what he had expected. He filed the report in the project folder, which was organized chronologically and by test type. He had been doing this for a long time. The folder for a typical project was orderly. The folder for a poorly managed project was not. His folders were orderly. The concrete continued to harden. Nobody watched it happen. It did not require watching. It simply proceeded, as chemical reactions do, according to the conditions available to it: the water in the mix, the temperature of the air and the ground, the cement content of the paste. These conditions were adequate. The hardening was adequate. The concrete was becoming what it was designed to become. Chapter 13. Perttee's opinion on admixtures. On one of the subsequent days, while they were preparing for a smaller pour a section of wall, nothing complicated, Perttee expressed his views on chemical admixtures. This was not unusual. Perttee had views on many aspects of concrete technology, which he expressed without urgency or dramatic emphasis, in the tone of a person describing established facts. His view on water-reducing admixtures, also known as plasticizers or superplasticizers, was that they were useful tools that were sometimes overused. A superplasticizer can significantly reduce the water content of a mix while maintaining workability, thereby lowering the water-cement ratio and increasing strength. This was a genuine benefit. The problem, in Perttee's view, was that some contractors use superplasticizers to make their concrete easier to pour and finish, without reducing water content effectively, using the plasticizer to achieve a higher slump rather than a lower water-cement ratio. This defeated the purpose. His view on accelerating admixtures materials that speed up the hydration reaction and increase early strength was that they were reasonable in cold weather, but should not be relied upon in place of proper cold weather protection. He had seen concrete with too much accelerator develop a rough, irregular surface texture that was difficult to finish properly. He did not like this. His view on air and training admixtures was uncomplicated. They were necessary for any concrete exposed to freeze-thaw cycling and unnecessary for interior slabs protected from weather. The small air bubbles entrained by these admixtures provide relief spaces into which water can expand when it freezes, preventing internal cracking. Interior slabs like this floor slab did not need this protection. He did not use air entraining admixtures here, and he was correct not to. Eno listened to Perttee's opinions on admixtures as he prepared the reinforcing bars for the wall pour. He agreed with most of them. He disagreed with Perttee's skepticism about shrinkage-reducing admixtures. He had seen them perform well in difficult conditions, but he did not say so, because there was no wall pour pending that would require shrinkage-reducing admixtures, and a disagreement without practical application was just noise. They did the wall pour. It went without incident. The wall was 200 millimeters thick, reinforced with vertical and horizontal bars connected to the floor slab through starter bars that had been positioned before the slab pour. The connection between the slab and wall would develop as both elements hardened. In the finished structure, they would behave as a monolithic unit. That was the intention. Chapter 14. The 28-Day Test. At 28 days from the date of the slab pour, the remaining 2 test cylinders were collected, transported to the laboratory, and tested. The procedure was identical to the 7-day test. The rate of loading was the same. The machine was the same machine recalibrated. The technician was, by coincidence, also the same technician. The first cylinder failed at a compressive strength of 31.4 megapascals. The second failed at 32.1 megapascals. The average was 31.75 megapascals. The specified characteristic strength for a C25-30 concrete on 150 mm cylinders was 30 megapascals. Both cylinders exceeded this value. The concrete complied. The report was issued and sent. Eno received it, read the numbers and filed it. He also calculated the 28-day to 7-day strength ratio. 31.75 divided by 20.0 gave 1.59. This was a normal ratio for ordinary Portland cement concrete, curing under these temperature conditions. Had it been significantly higher indicating slow early strength gain, he might have investigated the cement type. Had it been lower indicating early strength gain without commensurate late strength, he might have suspected inadequate curing or an unusually high water cement ratio. It was neither. It was normal. The concrete in the slab would continue to gain strength beyond 28 days, though slowly. At 1 year, it might have achieved perhaps 10 to 15% more than the 28-day value. At 10 years, a further modest increment, the rate of gain would diminish asymptotically. The concrete would not, in any practical sense, ever stop hydrating entirely, as long as unhydrated cement particles remained in contact with moisture. But the strength gains beyond a few years were too small to be of engineering significance. The structure would be used for its intended purpose. People would walk on the floor. Shelving units would stand on it. Forklifts, perhaps, if the hardware store required them. Snow, tracked in on boots in winter, would melt on its surface. None of this concerned the concrete. The concrete was not concerned with anything. It was concrete. The service life of a well-designed and properly constructed concrete floor slab in an interior, protected environment can be very long, a century or more, in many cases. This floor slab, assuming normal maintenance and no extraordinary events, would likely be there after everyone who had built it was no longer working in construction. Eno considered this occasionally, not with any particular sentiment, but as a factual observation about his trade. The things he made out lasted him. This seemed to him correct. Chapter 15. A Brief History of Concrete. Concrete is an ancient material. Though what the Romans called concrete, and what Eno worked with, were related more by principle than by chemistry. The Romans used a mixture of volcanic ash pozzolana, from the town of Pozzuoli, near Vesuvius, with lime and seawater to make a binder. The resulting concrete had remarkable durability. Structures built with it have survived for 2,000 years. The Pantheon in Rome, completed around 125 CE, has an unreinforced concrete dome 43 meters in diameter. It remains intact. Roman concrete's longevity was a subject of scientific study in the early 21st century. Researchers discovered that its durability was partly attributable to a reaction between the volcanic ash and seawater, which produced rare minerals that continued to strengthen the material over centuries. This was accidental from the Romans' perspective, but effective. Modern concrete, formulated for early strength and predictable performance, does not have these minerals. It compensates in other ways. The rediscovery of hydraulic cement that hardens underwater in the 18th and 19th centuries laid the groundwork for modern concrete technology. Joseph Aspin patented Portland cement in 1824, though what he patented was somewhat different from the material that would eventually bear the name. Isaac Charles Johnson developed a higher quality Portland cement in the 1840s and 1850s by using higher kiln temperatures. By the second half of the 19th century, Portland cement was being manufactured industrially and used in construction across Europe and North America. Reinforced concrete, the combination of concrete with embedded steel, emerged in the mid-19th century through the work of several inventors and engineers, including Joseph Monnier, William Wilkinson, and François Hennebeek. Hennebeek in particular developed a comprehensive reinforced concrete construction system that he promoted with considerable commercial energy. By 1900, reinforced concrete was being used for buildings, bridges, and infrastructure across much of the industrialized world. The theoretical understanding of reinforced concrete developed alongside its practical use. Engineers developed methods to calculate the stresses in reinforced concrete beams and columns under load. These methods were refined over the following decades, eventually leading to the limit state design methods used today, in which structures are designed to avoid both failure and unacceptable deformation under the range of loads they might experience during their service life. Eno did not think about this history often. He knew it, in outline, because a person who works with a material develops curiosity about its origins. But on a day of concrete placing, he was thinking about slump and temperature and finishing time and curing. History was not relevant to those questions. Chemistry was relevant. Experience was relevant. Attention was relevant. Chapter 16. The Site in Winter. By November, the project had progressed to the upper floor. The temperature outside was regularly dropping below 5 degrees Celsius and occasionally below zero. Concrete work in these conditions required additional planning. Eno ordered heated mixing water. The concrete plant heated the water used in mixing to approximately 50 degrees, which, combined with the heat of the aggregate and the cement, brought the concrete temperature at delivery to around 15 to 18 degrees. This was within the acceptable range. Concrete delivered below 10 degrees in cold weather was difficult to work with and slow to gain strength. He ordered a higher proportion of rapid hardening Portland cement in the mixed design. Rapid hardening Portland cement is ground more finely than ordinary Portland cement, which increases its surface area and therefore the rate of hydration. This allowed the concrete to gain strength more quickly, which was important in winter, because the sooner concrete reached a strength sufficient to resist freezing damage, the less protection it required. He arranged for insulating blankets to be available. These were rolls of foam-backed geotextile, 3 mm thick, sufficient to reduce heat loss from the fresh concrete surface significantly. After each pour, the blankets would be deployed immediately after finishing. They would remain in place for the curing period, which in winter was extended to compensate for the reduced hydration rate. The pours in winter went more slowly. Everything went more slowly in winter. The concrete was stiffer when it arrived. Finishing time was extended, because the concrete took longer to reach the right consistency. The crew wore heavier clothing which made movement slightly more cumbersome. The daylight was shorter. None of this was novel to Eno. He had done this before. He had done it before the weather forced the decision, and so everything was ready when it was needed. This was, in his view, the correct approach. Problems in concrete construction that were anticipated and planned for were not, in a meaningful sense, problems. They were tasks. Chapter 17. The Durability Perspective. Strength is not the only property that matters in concrete. Durability, the ability to maintain structural adequacy and functional performance over the intended service life under the expected environmental conditions, is in many ways equally important, and in some environments more important. The durability of concrete is affected by a number of mechanisms. Carbonation is when carbon dioxide from the air diffuses into concrete, reacting with calcium hydroxide and other alkaline compounds to form calcium carbonate. This process, over time, reduces the pH of the concrete pore solution from around 12.5 to below 9. At this pH, the passive oxide film that protects embedded steel from corrosion is no longer stable. Once the carbonation front reaches the steel, corrosion can begin, causing the steel to expand, cracking and spalling the surrounding concrete. Chloride ingress is another mechanism. In coastal environments, or where de-icing salts are used, chloride ions penetrate the concrete, and when they reach sufficient concentration at the steel surface, initiate corrosion even at high pH. This is why concrete used in these environments requires denser, lower permeability mixes, and why the depth of concrete over the reinforcing steel is specified to be greater. Freeze-thaw damage, as Perty had correctly noted, is addressed through air entrainment in exposed concrete. Sulfate attack, alkali-silica reaction, abrasion, and erosion are among the other mechanisms that can damage concrete in particular environments. Each requires specific mix design or detailing responses. The concrete in this building, an interior floor slab protected from weather, was not exposed to most of these mechanisms. Carbonation would proceed from the surfaces, but the reinforcing steel was covered by 30 millimeters of concrete sufficient for an indoor environment with low carbonation risk to provide many decades of protection. There was no de-icing salt exposure. There was no freeze-thaw cycling on the interior surface. The main durability challenge was abrasion, the wear from foot traffic, trolleys, and equipment over years of use. Eno had specified the mix to include a surface hardener, a dry shake of silicon carbide applied to the fresh concrete surface during finishing. This material, pressed into the surface by the troweling process, significantly increases the abrasion resistance of the surface layer. It would extend the service life of the floor considerably under the anticipated traffic conditions. It was a small additional cost. It was worth it. Chapter 18. End of project. The project was completed in February. The last concrete pour was a small topping slab on the roof, which served as a protective and waterproofing layer over the structural deck. It was a thin slab, only 80 millimeter, but it required careful detailing at the edges and penetrations to ensure continuity of waterproofing. Eno supervised the roof pour on a day when the temperature was 3 degrees, and there was a light wind from the northeast. He had covered all the adjacent surfaces with plastic sheeting to protect them. He had arranged for insulating blankets. The pour took 2 hours. The finishing was done by him and Perty and one other worker, a young man named Mikko who had been with them for 6 months and was developing into a competent finisher. Mikko asked questions. He asked why the screed had to be moved in a sawing motion and not simply dragged across in one direction. Eno explained that the sawing motion helped to consolidate the surface layer and to fill in any low spots more effectively than a single direction pass. He asked why the trowel angle changed during the different passes of the power trowel. Eno explained that the blade angle was nearly flat in the early passes to avoid cutting into the soft concrete, and became progressively steeper in later passes to compact and polish the surface. Mikko listened and nodded. These were questions that Eno had never been asked, and that he had never asked anyone, because he had learned them by watching and doing rather than by asking. But he found it straightforward to answer them. The reasoning was clear to him. He had simply never had occasion to articulate it. After the roof pour was complete and the blankets were deployed, Eno and Perty and Mikko had coffee in the side office. The calendar on the wall showed a photograph of a frozen lake in Lapland. The previous months had been used up, the pages hanging loose and turned. It was a practical calendar. The dates were printed large, and the spaces for notes were adequate. Eno had made notes on it in small, consistent handwriting: pour dates, temperatures, test results, delivery times. The project file was complete. It contained delivery tickets, slump test records, rebound hammer readings, compression test reports, site inspection reports, temperature logs, and the site diary. Eno reviewed it before submitting it to the project manager. Everything was in order. The concrete record was, in its way, a history of the building's concrete elements, the conditions under which they were made, the materials that went into them, the tests that confirmed they met their specifications. Someone, an engineer assessing the building for renovation decades hence, perhaps might one day read it and find it useful, or not. Either way, it was accurate. Chapter 19. What Eno knew. What Eno Inkinen knew about concrete, he had accumulated over more than 30 years of practice. It was not all theoretical knowledge. Much of it resided in his hands and his eyes, in his thumb pressed to fresh concrete, in the sound of the vibrator, in the particular gray of a well-mixed paste. This kind of knowledge does not transfer easily in words. It transfers through apprenticeship, through the repeated experience of doing the work and seeing the results. He had started as a laborer, moving aggregate and cleaning forms. He had become a finisher, developing the feel for when concrete was ready and how to bring a surface to the required condition. He had become a foreman, responsible for planning, quality control, and the work of others. He had worked on foundations, floors, walls, columns, beams, bridges, and industrial structures. He had worked with ordinary Portland cement, blended cements, self-compacting concrete, high-strength concrete, and fiber-reinforced concrete. He had made mistakes. He had once specified an incorrect water-cement ratio and caught the error before the pour, which was the correct time to catch an error. He had once failed to ensure adequate cover on a reinforcing bar near a form face, and the bar showed as a shadow in the finished concrete surface, which required remediation. He had once misjudged the set time of a finishing concrete on a very warm day, and the surface was not as well finished as it should have been. He remembered these mistakes. They had not happened again. What he knew could be organized into categories: materials, mixed design, placing, finishing, curing, quality control, durability, but in practice, it did not organize itself into categories. It simply functioned as judgment, the ability to see a situation and know what it required. This was, he understood, what experience meant in a practical trade, not the accumulation of information, but the transformation of information into reliable, situation-specific judgment. He did not think of his work as important in any large sense. Concrete was not a dramatic material. It did not draw attention. The famous buildings of the world were not, primarily, famous for their concrete. They were famous for their form, their location, their history. The concrete was simply the means by which form was made solid and permanent. It was the material that made things possible. It was not itself the thing. He was content with this. He had always been content with it, in the way that a person is content with a life that matches their temperament. He liked precision. He liked materials that behaved according to known principles, that could be understood and managed, that rewarded care. He liked work that produced visible results: a smooth floor, a plumb wall, a structure that would stand. Chapter 20. The hardening continues. The building opened in April. The hardware store moved in, arranging its shelving units and display fixtures on the concrete floor that Eno had placed the previous summer. Screws were sorted into bins. Drill bits were hung on pegboard. The owner of the store, a methodical man named Vinkropinen, organized everything with the care of a person who understood that a useful space required order. The floor was smooth and hard. The silicon carbide surface hardener had done its work. A pallet truck rolled across it without catching or roughness. Heavy shelving units sat on it without visible indentation. A worker who dropped a wrench found that it rang on the surface with a clean, hard sound and left no mark. Vin did not think about the concrete. He walked on it every day. He swept it. He mopped it once a week. He occasionally set a knee on it when reaching for something on a low shelf, and noted that it was hard, which was the property of concrete most directly experienced by people who work on it. He did not think about hydration, or water-cement ratios, or the development of CSH gel. He thought about inventory. Below the floor, the hydration reactions continued, very slowly, as they would for years. The unhydrated cement particles there are always some in any practical concrete, because complete hydration requires more water than is usually present, and the geometry of the microstructure limits access, continue to react with available moisture at a rate too slow to measure in day-to-day terms, but real nonetheless. The concrete was becoming very slightly denser, very slightly stronger over time. The change was imperceptible in any practical sense. Nobody would ever measure it in this floor. Nobody needed to. The floor was already stronger than it needed to be for its purpose. The additional strength gained over decades was a surplus that would never be called upon. This is the final state of hardened concrete, a state of quiet adequacy. It is there, bearing what it needs to bear, doing nothing dramatic. The chemical reactions have mostly concluded. The microstructure is stable. The reinforcing steel is protected by the alkaline environment. The surface is being worn at a rate so slow, it is measured in fractions of a millimeter per year. The structure stands. It will continue to stand. This is what concrete does, and it was what it was made to do, and in this there is a kind of completion, without drama, and without any particular need for attention.